Good morning, everyone. This is one more session with respect to Linux system programming. In this session, we need to discuss little bit more detailed about a shared memory segment. So before starting with the today's session, if my voice is clear, able to see the screen properly, please type 1 in the chat box. If my voice is clear as well as able to see the screen properly, please type 1 in the chat box. Okay, thank you very much. If able to recollect, what is the discussion happened in the last session? In the last session, we are trying to understand little bit detailed about message queue properties, and we are trying to understand how to achieve the full duplex communication using the message queue. That points we are trying to understand it. And can you tell me what is the purpose of MSG get? Can I say MSG get is useful for creating as well as opening, to create as well as opening. If already message queue is there with that key, it will open it simply. If not there, it will create as well as it will open. What is the return value of MSG get? Can I say you will get an ID? Again, what is the return type of MSG get? Answer is you will get an ID. What is the use of this ID? Using this ID only, we need to send message, we need to receive message. Again, using this ID only, we need to send the message and we need to receive the message. Now, what is the process if you want to send a message into the message queue? Will you agree? You need to declare one structure. The structure should contain two members. The first member will be long M type. Second member will be the data which you want to send. Again, is this correct or not? Tell me. Whenever you want to deal with a message queue, whenever you want to transfer the data into the message queue, two things you need to take care. You need to declare one structure. The structure should contain the two members. First member will be message type. Second member will be the data which you want to send. So will you agree? In this message queue, every message, not only the message, it should have the type of the message. It should have the type of the message. Now can you tell me, in the receiver section, if I write /RCV0, so which message the kernel will give us? In the receiver section, /RCV0, which message the kernel will give us? Definitely the first message, irrespective of the type, the first message the kernel will give us. Now /RCV, if I write 2 here, /RCV2, can I say the message whose message type is 2, it will give us? Can I say the message whose message type is 2, it will give us? Suppose if multiple messages are there with a type 2, if multiple messages are there with a type 2, can I say the first message it will give us? Can I say the first message it will give us? So such type of discussion happened in the last session. Such type of discussion. Now can you tell me /RCV, if I type -3, absolute value of -3 is 3, less than 3 is 2, 1. So which is the lowest type? In that first message it will give us. Such type of discussion happen. And MSG CTL function we are trying to understand. MSG CTL function to do some control operations on the message queue. To do some control operations on the message queue, we are trying to use MSG CTL function. To do some control operation on the message queue, we need to use One of the student is asking, sir, if no MSG type is less than 3, then what it will give? It will block. Try to understand. Try to understand. If in my message queue, there are 3 messages are there. First message is 5, second message is 6, third message is 4. D8F1, getting the point? In my message queue, there are 3 messages are there. First message type is 5, second message type is 6, third message type is 4. So if I write dot slash RCV 3 minus 3, now tell me, is there any message with less than or equals to 3 type? Less than or equals to 3 type? No. So then that MSG RCV function will block. Then MSG RCV will function will block. If you don't use non-block flag, it will fail. If you don't use non-block flag, can I say it will fail? Getting the point? B8F1. If that condition is not satisfied, if you don't use any flag, non-block flag, it will wait. This is a blocking function. I hope that point is clear. After that, we started thinking about one more IPC mechanism. We started thinking about one more IPC mechanism. What is that? We started thinking about one more IPC mechanism. What is that? That is called as a shared memory, which is called as the fastest IPC. Listen, which is called as the fastest IPC. Now, why it is called as the fastest IPC? In a today's session, we need to discuss it. Again, why it is called as the fastest IPC? In a today's session, we need to discuss it. What are the functions involved in the shared memory? IPC? One is SHM get function. Another one is SHM AT function. And another one is SHM DT function. And another one is SHM AT, SHM DT, and SHM CTL function. Again, the functions involved in this IPC mechanism: SHM get function, SHM AT function, SHM DT function, SHM CTL function. So what is the SHM get function will do? What is that SHM get function will do? I don't know you are following this material which we given a hard copy. What is the SHM get will do? Observe this. SHM, call the SHM get, create a new shared memory segment, or obtain the identifier of the existing shared memory segment. And this call return the shared memory segment identifier. So what is that SHM get function will do is, it will create a new shared memory, or it will obtain the identifier of the existing shared memory segment and returns that ID, like a MSG get. It will create as well as it will opening the existing shared message queue. Similarly, SHM get function, what it will do? It will create or it will obtain the existing shared memory segment identifier. Now, can you tell me where the shared memory segment is created? Can you tell me where the shared memory segment is created? Answer is, it is not created in a kernel space, it is created in the user space. Again, one important information I need to tell you, where the shared memory segment is created, answer is, it is not created in a kernel space, it is created in the user space. Try to understand this diagram. Try to understand this. So suppose this is the kernel space. Just a minute. Suppose this is the kernel space. This is the user space. Suppose that is a kernel space and this is the user space. Where the shared memory manager is there? shared memory manager. Where the shared memory manager is there, managers are present in a kernel space. Will you agree? Where the shared memory manager is there, manager is present in a kernel space. Okay. Now, when you create a shared memory segment, that segment is not created in a kernel space. The segment is created in a user space only. Again, when we create a shared memory segment, that segment is not created in a kernel space. that segment is created in a that segment is created in a user space. Shared memory segment. Every shared memory segment is having the two points. One is a key and another one is the ID. Again, every shared memory segment is having the two properties or two identifiers, two informations. One is the key and another one is the ID. Again, every shared memory segment is having the two things. One is the key and another one is the ID. Now, can you tell me in this program how much of shared memory segment I created? In this program, how much of shared memory segment I created? How many bytes of shared memory segment I created? In this program, how many bytes of shared memory segment I created? Will you agree? I created 50 bytes of shared memory segment. Will you agree? I created 50 bytes of shared memory segment. That segment is recognized with what? With what key? The segment is recognized with what key? Can I say the shared memory segment is recognized with the key number 3? So then what it will give us? Then what it will give us? Can I say it will give us an ID? Can I say this key is just for opening purpose? This key is just for opening purpose. Once we open the shared memory segment with this key, there is no further use of this key in a process. Again, once we open the shared memory segment with this key, further process there is no use of this key. In a further process, there is no use of this key. Key is just for opening purpose. Will you agree? Key is just for opening purpose. Now then what you will get here as a return type? What is the SHM get returns? Can I say SHM get returns one ID? Now, once you create a shared memory segment in a user space, you can't directly put the data into that memory. Again, try to understand the point. Whenever you create a shared memory segment in the user space, this memory, a process directly cannot access it. If any process wants to access that shared memory segment, the procedure is they need to attach the shared memory segment. Again, if any process wants to access the shared memory segment, what that process need to do? If any process wants to access the shared memory segment, what that process need to do? The process need to attach the shared memory segment. Like if you want to send a file in a mail, will you agree? You need to attach the document. Again, once you want to send a file through mail, so will you agree? In that mail, you need to attach this document. Similarly, here also, when any process wants to access this shared memory segment, the procedure is, the process need to attach the shared memory segment to this, attach the shared memory segment. If this point is clear, type C in the chat box. If any process wants to access the shared memory segment, that process need to observe this. Just a minute. Observe this point. Use SHM-AT to attach the shared memory segment, that is make a segment part of the virtual memory of the calling process. Don't worry, what is a virtual memory? So, if any process wants to use the shared memory segment, so then what is the step is you need to attach the shared memory segment. So, in this program, can you tell me in which line we are attaching the shared memory segment? Can you tell me in this program, line number is not displayed, right? So, will you agree? This is the line where we are attaching the shared memory segment. Will you agree? This is the line where this is the place where we are attaching the shared memory segment. Now you tell me, when you attach the shared memory segment, what you will get here? When you attach the shared memory segment, what you will get there? So can I say you will get an address? When you attach the shared memory segment, then you will get an address. So once you got an address, remaining process you know. Now like when you allocate a dynamic memory using the malloc, will you agree you will get one address? Again, when you allocate a dynamic memory using the malloc, will you agree you will get an address? So I hope all of you know how to access the data through that pointer, how to put the data, how to get the data. I don't know you're able to recollect it or not. When I'm dealing with a file handling using the C, there are so many. Sorry, when we are dealing with a dynamic memory, we discuss so many examples like how to allocate a dynamic memory for one integer, how to allocate a dynamic memory for five integers, how to allocate a dynamic memory for one string, five strings, n string. Able to recollect the point? Now here also the same thing. So it will give us one address. In that shared memory segment, what data you want to put, according to that you need to catch with that type of pointer. Again, in a shared memory segment, what type of data you want to put, according to that you need to catch the SHM80 return type. You need to catch SHM80 return type. Is that point is clear? Once you got an address, remaining thing is normal C program only. Once you got the address of that shared memory segment, remaining thing is what is that? Remaining thing is normal C program only. Now, if you don't want, now tell me, in a C language, you allocated a dynamic memory. You don't want that memory. What you will do in your program? In a C language, you allocated a dynamic memory. So after that, you don't want that memory. Your work is finished. So then what you will do? Will you agree? You will free that memory. You will free that memory. Here also, if you don't want that memory for you, you need to use SHMDT. If you want to free it, you need to use SHMDT, detaching the shared memory segment. Again, SHM80 is for attaching the shared memory segment. SHMDT is useful for detaching the shared memory segment. So once again, let's understand little bit clearly what is the meaning of SHM80. What happens inside when you use SHM80? So can you tell me every process is having, will you agree? Suppose there are two processes, P1 process and P2 process. Every process is having its own stack section. Every process is having its own stack section, its own data section, its own code section. Every process is having its own memory sections. Suppose this is a P1 process. Similarly, P2 process also. I'm trying to tell you what is the meaning of attaching the shared memory. I'm trying to tell you what is the meaning of attaching the shared memory. I'm trying to tell you what is the meaning of attaching the shared memory here. Suppose this is a P2 process. If this process wants to access this shared memory, will you agree? You need to use SHM80. If this process wants to access the shared memory, will you agree it need to use SHM-AT? So what happens SHM-AT means, in this process, virtual memory or heap section, memory is allocated, and this memory gets mapped. Again, what is the meaning of SHM-AT? Little bit detailed I am telling you. This memory and this memory gets mapped. There is a function in a kernel, there is a function that is called mmap function. There is a function called mmap function. So what is the meaning of attaching means, in a process space, user space, in a process space, some memory is allocated, and this memory and this memory and this memory is, what is that? Mapping is done. That memory and this memory is mapping is done. I'll tell you a very simple example. Suppose you have the WhatsApp group. In this group, how many members are there? Suppose, how many members are there? How many members are there? 4 members are there. So what happens in a WhatsApp server? One shared memory is going to be created. So this process can put, this process can put, this process can put, this process can put. Now tell me, in your mobile, when you are typing it, in your mobile, when you type the message, can I say that message will go to this shared memory? Actually, the data you are typing in your message, in your mobile, but the data will go to the shared memory. When the data goes to the shared memory, others can read that shared memory. When the data goes to the shared memory, will you agree? Others can read that shared memory. Can I say you are creating the WhatsApp group is nothing but, can I say you're creating the WhatsApp group is nothing but, in a WhatsApp server, for you some memory space is allocated so that you can you can you can you can not only you, your group members also can access that memory. Not only you, your group members are also can access the memory. So is it clear? What is the meaning of SHM-AT means? Whatever the memory is created using the SHM get, that memory, and in your process, one memory is created, this memory and this memory is gets attached. There is a function called mmap, memory map. Anybody knows something called carbon paper? Have you heard this term? Carbon paper. So for receipt, for bills, normally they will use it. Now tell me, there is on the top one paper will be there, back one paper will be there, maybe 1-2 papers will be there. When you type, when you write here, can I say that is reflected here and here? When you type here, that is reflected here and here. Similarly, what happens is, this is the shared memory. Yes, used to get a duplicate copy, correct? Used to get a duplicate copy. Similarly, here also, the process is putting the data into this memory, but that is affected here. That is affected there. Whenever you use SHM-DT, this memory is deleted, not the shared memory. Again, whenever SHM-DT, when you use, whatever the memory it is attached to you, that memory is deleted. Whatever the memory it is attached to you, that memory is deleted. So SHM-DT is not used to remove this memory. SHM-DT is used to, whatever the memory, duplicate memory is allocated to you, that memory is going to be deleted, not the shared memory. Similarly, if this process also wants to attach, can I say, For this process also, the attachment is done. All of you are getting the point? For this process also, attachment is done. Now, in this program, can I say, in this program, one process is writing the data into the shared memory. This process is writing the data into the shared memory, and another process, yesterday we shown you, another process is reading the data from the shared memory. One process is writing the data into the shared memory, another process is reading the data from the shared memory. So now any doubt is there till now whatever I discussed, please ask it. Till now whatever I discussed, if any doubt is there, please ask it. So one process is writing the data into the shared memory. Another process is one process is writing the data into the shared memory. Another process is reading the data from the shared memory. Yeah, I shared these two programs in a LMS yesterday. Yeah, I shared these two programs in a LMS yesterday. Again, I'm asking the question. Yeah, I shared these two programs in the LMS yesterday. Answer is yes. Yes, I shared it. So one of the student is asking one question, sir, when we use SHM-80, which address is returned, shared memory or heap? Good question here. Good question here. I need to clear that. What your friend is asking is, sir, whenever I use SHM-80, which address will I get? Will I get this shared memory address, or in a heap section, whatever the memory is created and mapping is done, that memory address? So for that, I'll show you. I hope all of you might have remembered how to print the address. What is the format specified to print the address in a C language? I hope all of you might have remembered what is the format specified to print the address. Percentile P, printf, printf, percentile P, /n, comma P. In the transmitter side, I am printing the P. In a receiver side also, let's print the P. In the receiver side also, let's print the P. Then you can conclude, are you getting the shared memory address or heap section address? Then you can decide it. In the transmitter side, in a receiver side, cc p1.c -o snd, cc p2.c -o snd, sorry, rcv. Okay, now observe /snd, hello world. And in the receiver section, let's see. In the receiver section, /rcv. Now you tell me, do you got the same address or different address? Who asked me the question? All of you are you observing here? Do you got the same address or different address? Do you got the same address or different address? Answer is different address. Now can you tell me, am I getting the actual shared memory segment address in this? Am I getting this shared memory segment address, or the memory which is attached to you, the memory which is allocated to you, that memory is which is mapped to here, that address you are getting? Can I say that address? Now SHMDT, will it remove this or will it remove this one or two? Can you tell me? When you use SHMDT, one is removed or two is removed? When I say two is removed, will you agree? SHMDT, it will not remove the one. One means that one, whatever you are observing there, it will delete the two. Is that point is clear? The process is one thing, one interesting point I need to tell you. One interesting point I need to tell you. The process is feeling that it is putting here. The process is feeling that it is putting here. But the process is putting the data here only. But whatever you write here, it is reflected here. BE8F1 is asking, BE8F1 is asking, sir, when the shared memory will be deleted? Are you talking about this one, BE8F1? Are you talking about this one? So this is in a user space. Where the user space is there? In a RAM or in a hard disk? Where the user space is there? In a RAM or in a hard disk? BE8F1. These are the processes are present in the RAM or in a hard disk. User space, kernel space is present in the RAM or in a hard disk. Shared memory manager is present in the RAM or in a hard disk. Can I say in a RAM? One thing is, when you shut down the system, this shared memory is freed. When you shut down the system, that shared memory is going to be deleted. Getting the point? When you shut down the system, that shared memory is going to be deleted. Second thing is SHMCTL ID IPC underscore RMID. Yesterday, able to recollect? MSGCTL to remove the message queue. Similarly, SHMCTL is there to remove the shared memory segment. Similarly, SHMCTL is there to remove the shared memory segment. And which command you need to use here? Which command you need to use to remove the shared memory segment? In a SHMCTL, which command you need to use to remove the shared memory segment? In SHMCTL, which command you need to use to remove the shared memory segment? IPC underscore RMID. So in that way, you can remove that shared memory segment. All of you are observing detaching the shared memory segment and removing the shared memory segment is two different points. All of you are observing removing the shared memory segment and detaching the shared memory segment are two different points. When you detach the shared memory segment from your process, can I say this is freed? When you detach the shared memory segment from your process, can I say this is freed? If you want to remove the entire shared memory segment which you created using the SHM get, you need to use SHMCTL and you need to use IPC underscore RMID. You need to use SHMCTL IPC underscore RMID. All of you are getting the point? Any doubt in this, please let me know. Any doubt in this, please let me know. So you are typing the message in your mobile, but you are feeling that your friend is in your friend mobile, the data will go. Again, you are typing the message in your mobile, the data will be in your mobile. From your mobile, it will go to the shared memory in a server. Will you agree? From your mobile, the data will go to the shared memory in a server so that others can access it. So that others can access it. So that others can access it. So this is about the shared memory segment. Can you tell me what is the disadvantage of this? Advantage is fastest. Why it is called as the fastest? Try to understand. one of the reason why it is called as the fastest, can I say? So there is no much involvement of shared memory manager. Again, try to understand very important point. Why it is called as the fastest IPC? Why? Because there is no much involvement of manager here. Second thing is, every transactions are in a user space only. So every time in a kernel space, data will not go from the kernel space, it will not come. Every time the data will not go to the kernel space, from the kernel space, it will not come. If you're getting the point, all the things, whatever you are dealing, all the things, whatever you are dealing here, all the things, whatever you are dealing here, can I say that is in a user space only? All the things, whatever you are dealing here, can I say in the user space only? There is no kernel space involvement. Again, all the things, whatever you are dealing here in a user space only. There is no kernel space involvement. Data is not going to the kernel space every time and coming back to the user space. Again, data is not going to the kernel space and coming back to the user space. Everything is in a user space only. Please reply it. Yes or no? Yes or no? So that is the reason this is called as the fastest IPC. And one thing is, everything is done in a user space. That is one of the reason. Second thing is, there is no much involvement of. Second thing is, there is no much involvement of. Second thing is, there is no much involvement of. There is no much involvement of. Hmm. There is no much involvement of kernel. But can you tell me what is the drawback of this IPC mechanism? What is the disadvantage of this IPC mechanism? The disadvantage of this IPC mechanism is if two processes are putting the data into the shared memory at a time. If two processes are putting the data into the shared memory at a time, can you tell me what happens? If two processes are putting the data into the shared memory at a time, can I say data gets mixed, data gets overwritten? If one process is writing, one process is reading, no problem at all. Try to understand the disadvantage of the shared memory. Advantage is it is the fastest IPC, no doubt about it. But when you think about the disadvantage of the shared memory, so if two processes are writing the data at a time, can I say data gets mixed here? Will you agree? If two processes are writing the data at a time, data gets mixed here. Again, if two processes are writing the data at a time, can I say data gets mixed here? Data collision happens here. Second thing is, suppose one is a transmitter, one is a receiver. Suppose one is a transmitter, one is a receiver. Who is a transmitter here? Who is a transmitter here? Which process is a transmitter process here? Can I say P1 is a transmitter? P2 is a P1 is a transmitter. P2 is a P1 is a transmitter. P2 is a receiver. Now my question is, whatever previous IPCs we discussed, whatever the previous IPCs we discussed, pipe, FIFO, message queue. In a pipe, will you agree, read will block when the pipe is empty? In a pipe, will you agree, read will block when the pipe is empty. In the FIFO also, will you agree, a read will block when the pipe is empty? In a FIFO also, a read will block when the pipe is empty. In a message queue, MSG RCV will block if expected message type is not there. In a message queue, MSG RCV will block if expected MSG RCV will block if expected MSG RCV will block if expected message is not there. But here not like that. Suppose transmitter is not kept the data here, but receiver came first. When I say receiver will get old data. Okay. So before transmitter transmit the data, if receiver receives the data, receiver will receive old data. Again, before transmitter transmit the data, if receiver receives the data, can I say receiver will receive, can I say receiver will receive the old data? Again, before transmitter transmit the data, if receiver receives the data, can I say receiver will receive the old data? This is one drawback. Second drawback is what? Second drawback is what? Transmitter before transmitting. Second drawback is transmitter before transmitting. If the receiver receives, second drawback is transmitter before transmitting. Second drawback, sorry. Transmitter and receiver both are putting the data at a time. Can you tell me? Transmitter and receiver, if both are putting the data at a time. Second drawback is when the transmitter and receiver both are putting the data at a time. So can I say data will be merged? So these are the two drawbacks. Can I simply say in this IPC mechanism, there is no synchronization concept. Now in a pipe already internal synchronization is there. Means read will block when the pipe is empty. Pipe and FIFO in both cases. Internal synchronization is there. Message queue also internal synchronization is there. MSG receive will block if respected message type is not available. But here there is no such synchronization mechanism. If I accept this point type 1, there are two major drawbacks of this IPC mechanism. First drawback is before transmitter transmit the data, if receiver receives, receiver will receive the old data or junk data. I'll have to copy this point. Before transmitter transmit the data, note it down. Before transmitter transmit the data, before transmitter transmit the data, if receiver receives the data, if receiver is trying to read, if receiver is trying to read from the shared memory, if receiver is trying to read from the shared memory, receiver will receive, receiver will receive, receiver will receive the old data. Second drawback. What is the second drawback? Note it down. Second drawback. If two processes are trying to write the data, second drawback. If two processes are trying to write the data into the shared memory, if two processes are trying to write the data into the shared memory, if two processes are trying to write the data into the shared memory, if two processes are trying to write the data into the shared memory, at a time. If two processes are trying to write the data into the shared memory at a time, data gets overlaps. Data gets mixed. Can I say? Data gets overlaps, or can I say data gets mixed? Again, if two processes are trying to write the data at a time into the shared memory, data gets overlapped, or we can say data gets mixed. In a simple and straightforward, can I say, in a shared memory segment, there is no internal synchronization concept. In a simple and straightforward way, can I say, in a shared memory segment, there is no internal, there is no internal, there is no internal synchronization. There is no internal synchronization. Will you agree? There is no internal synchronization mechanism. So if there is no internal synchronization mechanism is there, then can I say we need to use some other synchronization method? Will you agree? If there is no internal synchronization mechanism is there inbuilt, will you agree? We need to take the help of some other. I need to ask you, if in your microcontroller internal ADC is not there, then what you need to do? In your microcontroller, if internal ADC feature is not there, then what you need to do? External ADC. Similarly here also. Similarly here also. So in this IPC mechanism, shared memory, internal synchronization method is not there. So we need to take the help of some another synchronization mechanism. What is that? What is the next IPC? Semaphores. Getting the point? What is the next IPC? Semaphores. Using the semaphore, we are going to synchronize between multiple processes when they are trying to access the shared memory. Again, using the semaphore, we are going to synchronize using the semaphore, we are going to synchronize multiple processes when they are trying to access shared memory segment. Again, using the semaphore, we are going to synchronize multiple processes when they are trying to access the shared memory segment. When they are trying to access the shared memory segment. If this is clear, type C in the chat box so that we'll further move it. If this is clear, type C in the chat box so that we'll further move it. If this is clear, type C in the chat box. Okay, so before that, I'll create a situation, try to understand. Before that, I'll create a situation, try to understand. Just a minute. I'm going to create two programs. Observe what is the situation I'm going to create is. I'm going to write two programs. One is a W1, one is a W2. I'm going to write two programs, w1.c, w2.c. What this program is going to do is, it is going to put ABCDs, small ABCDs into this file. And what this program is going to do, it is going to put capital A to Z into this file. Again, I'm going to create two programs. So first program is responsible for putting small ABCDs. What is a memory here? File. Common memory is a file here. First program is trying to put small ABCDs into this. Second program is going to put capital ABCDs into the shared memory at a time. Can I say here the data must and should be get mixed? I'll have to copy this diagram, whatever I written with a annotate. I'll have to copy this scenario. I'm going to create two programs. What is the names of the program? I'm going to create two programs. What is the names of the program? One is w1.c, another one is a w2.c. One is w1.c and another one is a w2.c. I'm going to write two programs. One is a w1.c and another one is a w2.c. What is the job of a w1.c? The w1.c job is it need to put small a to small z into file, small a to small z into the file. What is the job of w2.c? What is the job of w2.c? What is the job of w2.c? It need to put capital A to capital Z into the file. Which file? Can I say both are putting the data into the same file? Both are going to put the data into the same file. Both are going to put the data into the same file. So will you agree, logically, will you agree the data is going to be mixed there? So then we'll think about how to synchronize this. Is it clear? First, let me clear this. Give me 1 minute of time. So here I'll write w1.c hash include header.h, w1.c hash include header.h, void main can I write here, this process is going to write small a to small z into file called data. File called data. Int fd. Fd is equals to open system call data file o underscore wr only o underscore create and o underscore append 0664. I'm using one mandatory flag, two optional flags here. Will you agree? I'm using here one mandatory flag, two optional flags. What is a mandatory flag I used? What is the name of the mandatory flag I used? O underscore WR only. Again, what is the name of the mandatory flag I used? O underscore WR only. What are the optional flags I used? What are the optional flags I used? Mandatory flags are WR only. What are the optional flags? Create and append. Create and append if FD is less than 0. If FD is less than 0, can I say it is a P error? P error. Open system call. Return it. Open system call and return it. Okay. Otherwise, for ch is equals to small a, ch is less than or equals to small z, ch plus plus, write fd ampersand of ch, comma 1 byte, and sleep of 1 second. Observe this for loop very carefully. I'm trying to write small a to small z after every 1 second into this file. Observe this for loop. I'm rotating the loop from a to z, and in this I'm writing small a to small z into the file after every 1 second. After every 1 second. Now what I'll do is, let me compile the code. cc -o w1 cp w1.c w2.c. What is the w2.c we need to do? What is the w2.c need to do? What is the w2.c need to do? Will you agree? Capital A to capital Z. Capital A to capital Z. After that, what we'll do is, just for the time being, just for display purpose, printf done. Just to display the work is done, I'm writing done there. Printf done. cc w1.c -o w1 cc w2.c -o w2. Can I say two executable files are ready now? Will you agree? Two executable files are ready. Two executable files are ready. Just a minute. Two executable files are ready. Control L. Now here ./w1. Can I say w1 is writing there, w2 is writing here? Sorry, ./w2. Can I say both processes are writing the data into the file at a time? W1 process and W2 process both are writing the data into the file at a time. Both processes are accessing the shared resource at a time. Both processes are accessing the shared resource at a time. So we can't expect the how the file looks now. We can't expect how the file looks now. Will you agree? Now observe VI data file. Can I say the data gets mixed? Will you agree the data gets mixed here? So logically think, we need one method to synchronize them. We need one method to synchronize them. So when one process is writing the data into the shared memory segment, another process should not write. Again, when one process is writing the data into the shared memory segment, will you agree another process should not write? When one process is writing the data into the shared memory segment, another process should not write. Again, when one process is trying to write the data into the shared memory segment, or here's the file. So this type of situations we can handle using the one of the IPC mechanism that is called semaphores. One of the student is asking, sir, how to know the process is writing? If you want, you use the return type of write system call. In all those programs, you use after write you use p error function. Is it success or failure? You will get it. D8F1, getting the point? Hmm? Now, will you agree? In this scenario, if one process is writing the data into the file, another process should not write. So, can I say I need to lock this file? This process need to lock this file so that another process cannot enter into this. So very simple. One method is one process should lock the file so that another process should not enter into that. So once this process is work is completed, what we need to do? Once this process is work is completed, what it need to do? Then I say unlock. So before the discussion of semaphore, we need to discuss about the concept called record lock. Again, before the discussion of the concept called semaphores, we need to discuss file lock, or we can call as file lock, or we can call as record lock. Is that point is clear what I'm saying? Before the discussion of semaphore concept, what is the concept we need to discuss? File lock or record lock, using file lock or record lock using FCNTL. Again, using FCNTL. Again, before the discussion of this, I need to discuss one another concept called F file lock concept. I don't know where it is. I'm searching here. Please give me 1 minute of time. Record lock. All of you getting this point? So before the semaphore concept, you need to understand this concept called a record lock, file lock, using which function? File lock using which function? using which function? File lock or record lock using which function? Please reply it. Record lock or file lock using which function? fcntl. Before that, I need to tell you one definition. Most of the interviews they will ask you, what is the critical section of code? What is the critical section of code? Answer is the part of the program we are trying to access shared memory or shared resource. The part of the program where we are trying to access the shared resource is called critical section of code. Again, the part of the program we are trying to access the shared resource is called as a critical section of code. All of you copy this. All of you copy this part. After copying, type C on the chat box. All of you copy this. After that, type C on the chat box. The part of the program where we are trying to access the shared resource. The part of the program where we are trying to access the shared resource. The part of the program where we are trying to access the shared resource is called as critical section of code. The part of the program where we are trying to access the shared resource is called as critical section of code. Now, can you tell me, in our program, which is the critical section of code? Observe, I'll show you this. Can you tell me, in this program, from which line to which line the critical section of code? From which line to which line we are trying to access the shared resource? From which line to which line we are trying to access the shared resource? Can I say from line number 16 to line number 20? Will you agree? From line number 16 to line number 20, we are trying to access. From line number 16 to line number 20, we are trying to access the shared resource. In another process also the same lines maybe. In another process also the same lines maybe. So the part of the program when we are trying to access the shared resource, from which line to which line you are accessing the shared resource, that is called as a critical section of code. Now, what is the topic we are going to discuss? Now, what is the topic we are going to discuss? Can I say the topic is record lock? Record lock is nothing but file lock using fcntl function. Record lock are also called as a file lock using the fcntl function. Will you agree? File lock using the fcntl function. So what we'll do is, this discussion we'll do it in a tomorrow's session. Is it clear? This is the program. If you have the time, you can go through this. So this we are going to discuss in a tomorrow's session. Okay, then. Thank you very much. I'm going to wind up the session. Thank you very much. I'm going to wind up the today's session.